Everybody, this new edition of the Ken Seminar Series, Fall 2021. I hope all the online attendees can hear us perfectly this time. And today is our pleasure to introduce Professor James Allison. So I'm gonna have to go through his bio for you to know a little bit more about his background. James Allison is a professor, the holder of the Jerry S. Drogobolny Faculty Scholar at the University of Illinois Urbana-Champaign, with joint appointments in industrial and systems engineering and also aerospace engineering. He earned degrees from the University of Michigan, the University of Utah, and Weber State University. As of now, his research develops quantitative methods for integrated system design with an emphasis on control, co-design, system architecture, and spatial packaging of interconnected systems. He has published more than 160 papers, and his methods are shaping engineering practice in renewable energy, aerospace, automotive, and other fields by enabling the discovery of high performance and non-obvious system design. So please join me in giving a warm welcome to Professor James Allison today. Use this microphone here. Or there are mics in the room, so we'll be okay to hear you.
Good, thank you. Thank you very much, Johan, for the introduction. Thank you for inviting me and organizing this. I appreciate it. I've not been to this building before, so that's a new experience. Today, I'm going to talk about one of the core concepts behind a lot of the research in my group and a lot of my colleagues' research, this idea of design coupling in engineering design or systems engineering. Just a little bit of background. I did grad school and postdoc at the University of Michigan. A lot of automotive focus, but other application domains as well. Mainly focused on working out how do we use optimization algorithms to help systems engineers do what they do in a better way. I worked at Ford doing engine design optimization, high fidelity modeling of engines. And then I worked at MathWorks in the Boston area, focused on simulating modeling basically, and how those models are used in systems engineering. Little bit with optimization, and then moved here. So to the ISE department, I focus on design automation research, a lot with design of actively controlled dynamic systems and some other things, as you'll see as we go on. So I'm going to talk briefly about what I mean by engineering system design research. It is a relatively new research field, and some folks may not be familiar with what does it mean to do research in this area. So there's a difference between engineering design practice, what engineers actually do, making decisions for real products or systems, and then engineering design research. We apply scientific strategies to generate new knowledge that helps engineers be better at design. Engineering design methods research specifically is focused on studying the methods, design methods or systems engineering methods that engineers use to create engineering systems products. And more specifically, I focus primarily on design automation methods that involve optimization and machine learning, perhaps other algorithmic techniques. The way I like to describe my research is as design method creation and analysis. Creating a method alone is not really fundamental research. We need to generate some knowledge about these methods. So we want to help engineers successfully design systems that are beyond current capabilities. Okay. In many approaches to system design research, we focus on the interfaces. There are other folks who focus very deeply on individual disciplines or design of certain subsystems or certain technologies. But there is a lot to discover at the interfaces within a system. So in this area, what does fundamental research look like? We want to produce generalizable knowledge. And you can kind of think of this in a way it's similar to control systems research. We're not focused on a specific application, but it's more methods driven. If you're a systems person, you've probably heard about the parable of the blind man, where as an individual, you can only get pieces of information about the whole. And if we're looking at an engineering system, it might look or appear to be different depending on who's looking at it. But through our integrated systems approaches, we'd like to get a better picture of the overall whole and use methods that help us to account more holistically for interactions or design couplings within a system so that we can improve our overall performance. So I run the engineering system design lab at U of I. And the two main areas that we work in are what some call control co-design or integrated physical and control system design. And also SPI2, it's an acronym for a very long term, spatial packaging of interconnected systems with physics interactions. So I'm going to talk briefly about each of these and how design coupling plays a role in each of these. In my group right now, we're down to about 6 PhD students right now and 6 undergraduate researchers. We're collaborating with lots of other people as well, not just my 6 PhD students. And there are many different degree programs represented in my group. Here's a collection of some of our application domains. We're very methods focused and more application agnostic, although there definitely is a flavor to what we work on, usually some kind of mechanical, mechatronic system, robotic systems, things that involve both key hardware elements and software elements as well. The kinds of problems that we tend to be drawn to are those that have really rich, interesting design spaces where there are opportunities to make new discoveries about how to arrive at new technologies or maybe new system configurations. Especially, we tend to focus on things that have the potential for high societal impact or non-obvious discoveries. And we often do collaborate with domain experts. I can't become an expert at everything, but I like to think we do a pretty good job at being the glue that brings together lots of other researchers from other domains. Here's one view, at least the way I think about research we do in my group. It's important for us to be plugged into engineering design practice. We need to engage with industry and get a sense of how they are actually doing their work and make observations regarding opportunities for improvement. And that's where the creative part of our work comes in. We might try creating new engineering design methods that maybe are, it's helpful for us to go through this process as an outsider. We might see things that people who are in the thick of the design problems might not see. Beyond that, we need to do some kind of analysis of these methods. This is largely an empirical process. We mainly do computational experiments. We do some hardware work, but it's mainly a demonstration that our design methods actually work in practice. So the empirical data we use is mainly derived from the computational experiments. And then ideally, we add to the engineering design body of knowledge, and it actually gets used and adopted in practice. And we have had a few experiences where our methods and tools are getting used in industry. It takes a very long time for that to happen. That's one of the main goals in my research, is to have a real impact on how systems engineering and design is done in practice. So let's talk about this concept of engineering design coupling and why is it important. When we're doing engineering design, or especially systems engineering, it often involves multiple design decision sets. What do I mean by this multiple decision sets? If we have design decisions to make about whatever the system is that we are developing, we could partition these decisions into different sets based on different criteria. For example, maybe we're thinking in terms of what are the physical subsystems that comprise a system. And maybe our human engineering organization is organized in this way, such that we have a group assigned to each one of these physical subsystems. And the systems engineer needs to figure out how to coordinate the activities of each of these different groups. And within each of these groups, they have their own individual design decisions that they need to be making. Another common lens to think about multiple sets of design decisions is disciplinary partitioning. So maybe we have decisions in each of these disciplinary domains for one of these subsystems in the physically partitioned approach. A lot of this is really an artifact of the human design organizations and how we've structured engineering knowledge. The boundaries of engineering disciplines has evolved over time, and that to me seems to be a synthetic artifact largely. And when we design a system, in reality, all of our decisions can be interrelated, and we need to figure out how to account for those interrelationships as we are making design decisions. So let's formalize this just a little bit. Let's suppose we have a system design problem that has at least two different sets of design decisions. Say if we're designing set if we ask this question, it helps us to start understanding what design coupling is. If we make design decisions or changes in one of those domains, do those decisions influence how we should make decisions in other domains to achieve our overall system goals? So suppose we have these two domains, each with their own sets of variables. Here, suppose this is an objective function that we want to minimize or minimize. It depends on those sets of design variables. So for example, if we specify the design in domain A, we'd like to answer how should we design domain B to obtain the best possible design, minimizing or maximizing f of x. So given a value for A, we should choose a value for B that solves this problem. So the design variables for A are fixed, but we're adjusting the design variables for B to find out what gives us the best overall system performance. So that is, given a value for x of A, we choose the design for B to be this XB star, the star asterisk, indicating that's the optimal value. So with that background, then we can define what we mean by design coupling. So back to this original question, if we change the design in domain A, how should we design in domain B from an optimization perspective? Suppose we have a change in design A, we can then find out what is the best decision in design domain B. And we can quantify the strength of the coupling between these two domains by calculating sensitivities. In the simple scalar case, if these are just single scalar values, then this sensitivity gives us what is the strength of the relationship, at least in one direction, between domains A and B. We can also reverse that or invert that sensitivity to get the coupling strength going in the other direction. Something to keep in mind is, of course, as we move through this combined design space in the XA and XB directions, the value of the sensitivity in general can change. Most design optimization problems for engineering posed this way are nonlinear problems, and these sensitivities can change. And that's part of our current research, is looking at how can we account for the global nature of these coupling strength sensitivities and use that to inform a variety of things, including how we might go about the actual optimization process or extracting qualitative insights from this kind of quantitative information that we get through these studies. I need to update this graphic, but here's a very simple example. Say we have an energy harvester, some structure that is moving here with a prescribed motion. We have a mass spring system, and then some kind of generator that can exert a force and extract energy out of the system. And if we have a specification for the stiffness of the system A, then we can ask this question: what's the effect of varying Kc, which is, you can think of as a control gain? How aggressively should we be extracting energy out of the system? When charging or generation is less aggressive, increasing this gain will initially increase the force, which increases instantaneous power and the energy harvested. However, if we keep increasing how aggressively we're extracting energy from the system, eventually it's going to reduce amplitude, reduce velocity, and the energy starts to drop off. The same argument can be made from the other direction, increasing stiffness or a fixed value of the control gain. In this problem, there is present what we might call analysis or physics coupling. And I think it's important to make a distinction between analysis coupling and design coupling. They're related, but they are two different concepts. So if we have this physics coupling present in a system like this, for example, this means that our mechanical behavior influences the electrical system behavior and vice versa. So if we have models of the overall system, then we might have a coupling of state variables, for example, between these two aspects of the system. That's different from design coupling, but if we have this sort of physics coupling, it often does give rise to design coupling. Here, in this case, we have bidirectional design coupling, and a way of thinking about that is for a given value of stiffness, what's the optimal gain for the controller for a given control design, what is the optimal stiffness for the system, and then we can quantify those sensitivities, thinking about each direction using those values. And of course, this is a super simplified version of the problem where we only have a single variable in each domain. Things get a lot more complicated as well. Often we do work in open loop optimal control, and so we're not using scalar parameters for our control design, but rather trajectories, function valued quantities. That makes things a little bit more interesting. Here are some of the more complete quantifications of design coupling. If we have multiple variables, then we really have a whole matrix or Jacobian that describes this. And this Jacobian can change over the design space. So it is a really complicated quantity, but it can provide value in different ways. We might be able to identify maybe there are relationships that are not quite as important, and then instead of solving a problem all simultaneously, we could break it up into sub-problems and solve them in sequence in a way that ignores some of the couplings, but not all of them. Here's a way of thinking about possible design solution approaches. A conventional sequential approach, which is what typically happens in practice with an engineering organization designing some kind of actively system. You have the folks who are experts at designing the physical system, whatever it is, and then they hand that off to the controls engineers to try to get it to work right. And the controls engineers often end up frustrated. And this is part of my background as well, where I had this really great opportunity while working at MathWorks, where every day I ended up talking to controls engineers, mostly in the automotive and aerospace industries. But I got to see the perspective of controls engineers and their frustrations with how difficult it was to get these plants, these physical systems to work and meet requirements. And they wish they could go back and change things. But it also got me thinking, are the controls engineers necessarily the best people on their own to say what's the best way to design the plant? Really, we need to study the interface. It's not just the mechanical engineers or the controls engineers who are the right people, but we need people who understand the interface between these two domains. One approach to solving this, and in practice, this is often what happens if there is something that, well, maybe we can't meet requirements through control design alone, we have to go back and make some modifications to plant design. And if we take this process and map it over to design optimization problems, mathematically, we can show that this does not always converge to the system optimal solution. That it requires a simultaneous approach where we are making decisions about all aspects of the system simultaneously. There are some mathematically equivalent problem formulations, or they're equivalent to the simultaneous design approach, and that's one aspect of our research, is to try to find good formulations that are equivalent to this simultaneous problem, but might be numerically easier to solve. So this simultaneous approach, it fully accounts for design coupling, but it requires a bigger investment to use this approach, whether we're thinking in terms of a human design effort or in terms of design optimization. This means we have to fully coordinate all of the decisions simultaneously. And in standard systems engineering practice, we tend to like to decompose things or make problems modular and have well-defined interfaces. And yes, we can account for some coupling with that approach, but this completely holistic simultaneous design approach really conflicts with standard systems engineering practice. Systems engineers, they need to do this careful coordination and balancing of conflicting trade-offs, but this is made extra challenging when we have strong design coupling that crosses multiple areas within the systems engineering effort. If we can do design coupling analysis and identify some of these sensitivities, that can help us in determining what aspects of this coupling are most important to coordinate explicitly. A good understanding of the coupling within the system design problem, as I mentioned before, can help us in generating design optimization studies that perhaps take advantage of weak versus strong couplings in the overall system. And maybe we can have some kind of sequential approach, for example, that is easier to solve. Perhaps the most valuable aspect of this kind of analysis is it can reveal what we call synergy mechanisms. So I've defined design coupling, but the presence of design coupling provides the opportunity for us to take into account complete relationships within the system design problem and ideally describe these in a qualitative way that helps engineers who are leading aspects of the system design problem to do better with their problem. I do a lot of work in wind energy system design, and one of the main folks who's been an advocate of using these more integrated approaches, wind energy systems, he describes an interesting synergy mechanism qualitatively that this person is the current RPE program director, Mario Garcia Sanz. And he intuitively years ago latched on to this particular synergy mechanism that got really excited when the work from my group was able to formalize and help us approach this in a quantitative way. So one of the basic synergy mechanisms in a wind energy system is a standard controller for controlling the generator. The turbine uses maximum power point tracking. Essentially, we can use a simplified model of the system and determine what should the resistance torque of the generator be, the blade pitch, so on, to maximize how much power we're extracting out of wind at any given point in time. And that's great, but that can result in really high loading, pretty significant fatigue damage to the structure, to the gear train especially. And his strategy years ago was to try to shave off some of the peak loading in a really strategic way and give up a little bit of the energy produced, but that allowed him to dramatically reduce the cost of the structure, the tower, the powertrain. And if our overall system design goal is to reduce cost of energy, then there was a net benefit. So with these kinds of analyses, looking at different types of design coupling within a system problem, that gives us the opportunity to identify these more complete relationships or synergy mechanisms like the one I described with wind energy. Okay, control co-design. And looking at the time here, talking a lot. There's a lot of interesting stuff that we can go through with control co-design. I want to make sure that we have a little bit of time for questions. I've already described my combination of experiences. So I was trained in my PhD as an engineering system optimization person, but then my industry experience also really contributed to the ability to frame this problem and help us have some success. And through both these RPE projects and others, we've come full circle, and now some of the tools coming out of my group are being used by large companies in designing wind energy systems. So this other area I want to talk about, SPI2, spatial packaging. This is another one that involves some really interesting complex design couplings. And it involves the design of pretty much any kind of interconnected physical engineering system where you need to fit stuff in some kind of constrained space. And there are physical aspects to the problem too. It's not just geometry, but maybe heat transfer is important. We've had a range of support for this work, starting off with initial support through the NSF POETS ERC. And then we've worked with lots of other companies. We had a DARPA project on this, for example, and it was also a strategic research initiative from the Granger College of Engineering. Let's see. I think I've pretty much covered that. Okay. I mentioned earlier, one of the things we do is look for mathematically equivalent optimization problem formulations, things that are equivalent to this ideal simultaneous design that might be easier to solve. Nested design optimization is one that tends to be really helpful. For example, if we nest our control optimization within our plant or physical design optimization, then we can take advantage of algorithms that are tailored for solving the optimal control problem. And that has tended to be very successful, perhaps in the majority of the problems that we work on. Here's just a quick slide showing the basic formulation that we use when we use direct optimal control, open loop optimal control methods. We presume we have some system objective function that we want to minimize with respect to our plant and control design variables. We have the optimization not only look at what are the optimal design values, but also resolve the dynamics of the system through constraints on dynamic, basically physics constraints. We often will have path constraints. These are really important in things like failure modes for the system, looking at temperature limits, stress limits, those kinds of things. So resolving those path constraints are quite important. We can also derive optimality conditions for this formulation, but most often we have to solve these numerically, of course. A couple of examples from control co-design. One is in spacecraft attitude control. The local news here, WCIA, is actually leading up to Laura Waldrop's NASA mission. They interviewed me about this attitude control technology, and it aired on Monday. But the basic idea is we have a lot of distributed mass in a lot of spacecraft, either solar arrays or antennas. And we could use that mass to our advantage. We've been working on using piezoelectric strain actuators distributed across appendages, whether arrays or antennas, and bending those arrays, and with conservation of angular momentum, using that as a way to orient or point the spacecraft bus, the main vehicle. If this is a space telescope or a communications device, then that pointing accuracy is really important. So we boil this down to a distributed control and distributed structural design problem. And with control co-design methods, we found some really interesting tailored shapes that get us the best passive dynamics that synergize with the active control of the system. And this also led to a new discovery that not only helped us to get fine pointing precision, but just with the piezoelectric actuators, nothing else, no flywheels, no thrusters, we can get complete slew control or rotational control of spacecraft without using flywheels. Let's see, that video is not working. So this right here is a spherical air bearing, and balanced on it are these two PCBs with batteries on the end, but there are piezoelectric actuators on the printed circuit boards that allow us to extend, contract, or bend. And essentially what we're doing is we're going through a cycle where we bend the arrays, and that causes a small rotation of the bus, but then we pull in the mass that reduces our mass moment of inertia, then we bend back and then extend back. So it's kind of like how if a cat is falling through an air or falling through the air, it goes through a similar sort of pattern of motion to right itself. And it's been a challenge. We've had NASA proposals rejected because folks think this violates conservation of angular momentum, but it doesn't if you consider the full nonlinearities of the system. So there's a spin-off company now that's commercializing this. They're slated to have their first test flight low Earth orbit in early 2026 and their first commercial flight in 2027. So this is a nice success story from application of control co-design strategies that led to a discovery of a new technology that's now being commercialized. I think I'll skip through the history of control co-design. Basically, we made some breakthroughs in how to formulate and solve the problem that made a big difference in the methods from the world of design optimization actually being useful for design practice. Previously, the methods made a bunch of simplifying assumptions and it was not really practical. But we bridged that gap and now these methods are being used in practice. Okay, maybe I'll just very briefly talk about SPI2, what these systems are. Any kind of system where you have a bunch of stuff that needs to be packaged into a tight strained space, and you have interconnects that are of non-trivial size. Maybe it's electrical cabling, piping, or tubing. And when it comes to actually designing these kinds of systems in industry, there's always a manual component. There's a lot of stuff we can automate, but until recently, this aspect of design has never been automated. Yeah, so we've had lots of, well, let's see. Those are some of the main challenges, especially thinking about what's best for the overall system. Here are some examples of SPI2 applications across lots of different domains. As I mentioned before, we have lots of great tools that help support design decisions, but we don't have any design automation, or until recently, we didn't have any design automation for these SPI2 design decisions. It all boiled down to an engineer sitting at the CAD application, trying to work out where's the best way to put these components and the interconnects while accounting for things like thermal interactions, electromagnetic interference, other things. So it's kind of like using really advanced manufacturing, right? Making an analogy here. We have really advanced design tools, but really simplistic design when it comes to making SPI2 design decisions, sort of like having really advanced robotic manufacturing, but in the end, using hand forging to do the final assembly. Here's an image from a submarine. One of my current PhD students used to work at Electric Boat. He came to work in my group specifically because he was really frustrated with the design practices for submarines, where it's really just through manual trial and error that they figure out how to assemble these really complex systems. Back in the 1950s, they would do full-size wood mock-ups to make sure everything fit as they hoped. They transitioned to CAD in the 90s, but they're still kind of stuck there. Let's see. Basically, there's been a lot of work done in pieces of the SPI2 problem, such as the geometry-only problem for packing, the interconnect routing problem, bringing in multi-physics into the problem. And each one of these elements is really challenging on its own, but bringing it all together is an extremely difficult problem. One of the big issues is resolving or navigating a certain type of topological decision. Here's one of the main concepts. Suppose you have an interconnected system. The connectivity doesn't change between these two arrangements, but the spatial topology does. So here, if we were to try and transform this topology to this topology, we would have to make a cut and rejoin the interconnects. And navigating the different options for spatial topologies had never been incorporated into SPI2 system design before. There's another example of two systems that have the same interconnect configuration but different spatial topologies. And this challenge was to formalize these decisions mathematically so that we could incorporate it into design automation. So we did have some recent breakthroughs in SPI2 design. We had this workshop back in 2018 that really helped formalize the problem and helped me to understand the potential impact of it. We had a lot of people who were very interested in getting a solution to this problem. So we were looking at how to represent these spatial topological decisions mathematically. We ended up working with Professor Nathan Dunfield at U of I in mathematics. He's an expert in topology, knot theory, rate theory, these sorts of things. And it was a really exciting opportunity to take results from pure mathematics to make something completely new possible in engineering design. One of the solutions that we discovered worked really well is something called the Amada polynomials. Essentially, we can take a 3D representation of our system, project it onto a plane to make what we call a spatial graph. And then by tracking all of the crossings, it produces a polynomial that we can operate on algorithmically. So I think that's the main point to get through. We've done a lot of stuff with it with simplified systems. We've worked with Ford, we've worked with Toyota, we have a DARPA project on this. We're looking at other domains, including photonics as well, bringing in different sorts of physics. Yeah, you can see some of the folks that we've worked with, some of our collaborators. There's a website for SPI2, and we have a Python-based open source tool. It's not quite as capable as our research code, but there's a basic framework that's available for solving these problems. We're starting to look more at whole life cycle considerations, things like assembly and disassembly, both with human assembly and robotic assembly, more general components, and integrating additional physics into the problem. A really challenging thing is dealing with flexible interconnects. For example, Tim Brettel in aerospace, he's a roboticist who looks at manipulating flexible objects of different types. And could we take into account what is possible as far as assembling these flexible components with robotic systems and making decisions about how to design these SPI2 systems? We're using machine learning and other strategies to scale these beyond the basic algorithms that we started out with. Okay, I'm going to leave at least a few minutes for questions and discussion. I went through SPI2 pretty quickly, but maybe just tie things together with this conclusion and see what questions are now. If we can explicitly consider and analyze design coupling that's present in engineering system design problems, that can really provide some advantages in systems engineering and design activities. We've developed new, more integrated system design strategies, control co-design, SPI2 methods that help us to more fully leverage design coupling to provide value both to the engineering organizations solving these problems and to society. And if we learn how to better focus on system interfaces from a design perspective, perhaps there are new possibilities that we'll discover in the future beyond control co-design and SPI2 that could help us to do a better job with design of complex engineering systems. All right, so with that, I'm going to conclude and see if anyone has questions, see what you guys want to talk about.
Thank you so much for the presentation, Professor Allison. There's been a lot to cover, so let's ask the audience if anybody has a question to formulate right now.
Yeah, please.
Thank you for the presentation. You had a slide where you showed there's a plan team and there's a control team, and the conventional way is plan team design something and the control team
Right.
now it's their problem. And then in the end, you sort of converged on, well, maybe the best way to do this is like the design and the controls happen simultaneously. So you're saying that you found a way to mathematically formulate this problem, and I guess I'm trying to understand, like, is the human factor like taken into this formulation?
Yeah, that's a really good observation. A lot of what I presented here assumes engineering design optimization mindset. But engineering design optimization problem is really just a model of the real engineering design problem.
Right.
Real humans making the final decisions. So these optimization problems are really just decision support tools. It's an abstraction of the real problem. And so there are differences. So if we make this abstraction and we define our problems as optimization problems, then we can prove things about whether something is system optimal or not. But we might not, in our optimization model, have all the elements that we might need to consider or in other words, the optimization problem formulation might not be entirely accurate. So that has to be used the results from the optimization studies, the engineers making the actual decisions need to keep in mind that there are some simplifying assumptions in there. Yeah, so at least I've not really incorporated the human factor directly into the optimization studies, but I think it's very important to be aware that there can be a chasm between the mathematical optimization studies and what the engineers should be doing in their design activities.
I just have a small follow-up on
Yeah,
that.
yeah.
When it comes to next generation products, oftentimes design teams don't know what they're doing. They're just trying stuff. So if there's like a cookbook on how to do this, but at the same time you're developing something that maybe doesn't really exist, or it's like super next generation, how does that like work?
Yeah, this is a really tough problem. So if you talk to a typical design optimization person, I think they will overestimate the value that design optimization could provide. So they might think of this as, well, this is a great opportunity if we can do a clean sheet design, start from scratch, and just let the algorithms tell us what's best. Maybe there are some specific circumstances where our physics modeling is complete enough, our assumptions are not too strong, that actually deliver these kinds of results. And there was a DARPA program that actually focused on this. So the director's name was Jan van der Brand, and he wanted teams to solve these big challenges, including locomotion challenges. Take this object from Washington, DC and move it to Boston. Go. So they wanted completely open-ended, clean sheet designs. But it was a huge challenge. In reality, there are so many unknowns with engineering. We don't know what all of the failure modes might be in unprecedented designs and in next generation systems. So it's complicated. I think we need a combination of maybe very broad clean sheet types of exploration, but we also need actual hardware testing and realizing what is practically possible. And then that can go back and inform, well, maybe we overlooked an important failure mode or another important physics mechanism, and put that into our models and then come up with something more realistic. Yeah,
Thank you. Is there any other question in the room? Well, I will allow myself to ask you a question. The slide where you were presenting about this Yamada polynomial, to me is quite interesting. And I get the fact that you want a mathematical formulation to optimize spatial distribution. But then I would like to ask you, what is the current practice? What is the state of the art? Because in most devices that we get or vehicles, when you get to see the inside, it looks quite clean, although I have no expertise on this. But what would be the approach that they are following right now to get these layouts so far?
Well, so common practice is it's done manually in some way. There are some specific cases where there are design automation tools like VLSI, very large scale integrated circuit design, but those require lots of simplifying assumptions. We're only dealing with planar designs. We're using Manhattan rules on a grid. And these are really powerful tools that make it possible to design really complex systems. But they only work with those assumptions. But if you're trying to design a more three-dimensional system, like under the hood of the car, that's an entirely more complicated problem. And so it's really only been the last few years with our design automation tools for SPI2 that it's been automated at all. As far as I know, it's really only our direct collaborators and others who've started using our tools that are doing something other than manual design.
And how is that you can go back from a 2D projection to the 3D optimization when you formulate a problem?
Yeah, that's really interesting. If I go, well, let's see. I'll just describe it verbally. So we take the 3D information, project it onto 2D, but in that projection, we take note of what are the crossings. So does this interconnect go over or under this other crossing? And then there's a formalism for tracking that. And with that information, then we can form the Yamada polynomial. And of course, the projection, it depends on what orientation the 3D system is. And if you take different orientations, take different projections, the form of the Yamada polynomial will be different, but it will be mathematically equivalent. You'll be able to show that those resulting polynomials are the same. So it's kind of like isomorphisms in graphs. So we have a way now of checking if we have a unique spatial topology, and that's an important thing in exploring the spatial topological design space.
Thank you very much. We have any other question in the room? Well, if not, all that is left for us is to thank Professor Allison for being with us today. It's been a pleasure to host you, and we look forward to having you in an upcoming edition of the Ken Seminar Series. So thank you so much again.
Yep, thank you. Yes.